Okay, 3.3, long division, synthetic division, remainder, and factor theorem. All right, so long division of polynomials, really we're just, we might, hopefully we remember how to do long division. If you remember, if you have something like this, you say 46 divided by 5, right? Just to get the terminology down, what's underneath the division sign is called the radicand. No, I'm sorry, it's called the dividend. This is the dividend, this is the divisor, and up here is going to be the quotient. So this is called the divisor, the dividend, and what we're going to get up here is the quotient, plus any remainder. So if we did that, remember back in arithmetic class, we said, okay, 5, if it went into the number, it goes in 9 times, right? 9 times 5, and we would then multiply and put it here and subtract, and then we could see that it doesn't go in anymore, so we would say here 46 divided by 5 equals 5, and a remainder of 1, which we would put over the divisor. Right, so that's the idea of long division. And it's the same thing when we're dealing with polynomials. We're going to have a dividend, and it's going to be divided by a divisor, and it's going to equal a quotient plus a remainder over the divisor. Okay, that's kind of called the division algorithm, which is nicely stated for you also on page 367. And you can rearrange that equation any way you want. You can say dividend divided by divisor. Notice, if you recall, I say 45 divided by 9, we know is a nice equal 5. In reverse, we can always say 5 times 9 equals 45. Right? That's a relationship that's always going to hold. And that's the same when we deal with polynomials. If we get a quotient with no remainder, in this case we call 5 a factor, or we call 9 a factor of 45, and 5 a factor of 45. And this is really the most important part of this section is coming up with factors of the polynomials. If you recall in section 3.2, we were finding zeros of polynomials by finding the linear factors. And when it becomes a little bit more difficult with higher degree equations or higher degree polynomials, we have to find a way to break it down into its linear factors in order to find the zeros or the x-intercepts of the function. So that's where this is going to come into play for us. When we look at numbers, we have 45 divided by 9 equals 5, so this relationships hold, and we call 5 and 9 factors of 45. So the same idea is going to hold for polynomials. So we're going to go through a long division process, and then we're going to do a little shortcut method, but the shortcut method will only be applicable in certain situations. So let's look at number 4 on page 373, and we have a third degree polynomial here. And we're dividing that by a binomial x minus 3. Okay, so this is the dividend, and this is the divisor. Right? Coming back here, we have the dividend divided by the divisor. We want to come up with the quotient and a remainder if there is one. So just like old time division, we set up the division sign. Let me put this over here so we can have some more room. And we put the dividend underneath the division sign. And we want it to be in descending order. Again, remember descending order from 3.2, highest exponent first, next highest, constant term. Now it's also very important in these problems that if there's a missing degree term, you want to put in a 0 for that missing degree term. So if it was just x cubed minus 5x, we would want to put a 0x squared in there just to hold that place, because the place we put our numbers is going to be important when we do this long division. Alright, so we have our dividend in descending order and our divisor on the outside. So our method here is we take the first term of the dividend and divide it by the first term of the divisor. So we're saying x cubed divided by x. Now if you need to write that out, x cubed divided by x, we know our rules of exponents, 3 minus 1 gives us x squared. Right? So first term of dividend divided by first term of divisor is x squared. You put that over the same degree term here. That's why we want to put that 0 in if there is no 0. So we put the x squared term in above the x squared term in the dividend. And just like we multiplied over there when we were looking at numbers, we do the same thing here. We multiply this by the divisor and we put it here. So x squared times x, and put that under the same degree term. X squared times negative 3 is negative 3x squared. I'll put that in parentheses because you're subtracting all of that from the original dividend. So we're subtracting x cubed from x cubed. We get no x cubed terms. We're subtracting a negative here, so we're adding 3x squared to negative 2x squared to be left with positive 1x squared. And then we bring down the rest of the dividend and repeat the process until the first term does not divide into the first term of what's left anymore. Here we have a higher degree here than we do here, so we can go another step. When you get down to just a constant term here, then that's going to be your remainder if there is one. So we repeat the process now. First term of what's left divided by first term of the divisor. X squared divided by x gives us x, positive x, so we put the positive x up there in our quotient. X times x gives us x squared, and x times negative 3 gives us negative 3x. Again, good idea to put that in parentheses to remind yourself that you're subtracting the whole thing. X squared minus x squared, no x squares. Negative 5 plus 3x gives us negative 2x. And again, we have the same degree here as we do here, so we can go one more step. Negative 2x divided by x gives us negative 2. Negative 2 times x. And nicely here we're going to see we do not get any remainder. That kind of makes things a little bit easier. So this would be our remainder, if we had one. In this case, our remainder is 0. So if we go back to the division algorithm, we had our dividend divided by divisor, dividend divided by divisor. We would say this equals the quotient. This is the quotient, x squared plus x minus 2. And then if we had a remainder, we don't, we would put that remainder over the divisor. We don't have a remainder, so that's our answer. Now again, like you said, since 45 divided by 9 is 5, we can multiply to make sure we got it right. So if this is true, then this times this. Since there's no remainder, we can now say this is a factor of this, right? Because there was a 0 remainder. We can say this times this should be this. I'll leave that for you as a check, but it will come out. If you multiply this times this, you'll see that you get back the dividend. All right, so that is long division. So now there's an alternate method called synthetic division. But it's only available to us only can be used when the divisor is of a certain form. Okay, so either x plus a number or x minus a number is this form, right? If it's x plus a number, then the c would be negative. If it's x minus a number, then the c is going to be positive, right? So if the divisor is in that form, we can use this synthetic division. So let's look at an example of this using the one we just looked at. Since our divisor in that case was of the form x minus c, it was x minus 3, right? So looking at the same question, this is our dividend and this is our divisor. So here our c value would be 3 in the x minus c form. So using synthetic division, okay, I'll rewrite it here just so we have it all together. Minus 5x plus 6 divided by x minus 3. Okay, so this is of the form, okay, this is with c equaling 3, right here, x minus 3. So what we do here is we set up a little box in an upper left-hand corner of what we're going to do. And in that box is where you're going to put the c value, whatever that c value is. So in this case, the c value is 3. So we're going to put a 3 up there. And then, again, this is why it's very important to have your dividend in descending order and zeros put in for any missing terms. Again, here there are no missing terms. So we're just going to put the coefficients of these terms. We're going to leave the x values out. All we need are the numbers in front of the x's. So a 1, a negative 2, a negative 5, and a 6. And we're going to write that left to right next to this box with the c value. So 1, negative 2, negative 5, and 6. And then leave yourself enough space for another line of values and draw a line under that. All right, now the synthetic division approach and the steps for this are listed for you on page 369. We'll use those steps here. What you do is you take that first number, whatever that first number is, and you bring it down here. So positive 1, we drag that down underneath the line that we drew. Now we take this number and multiply it by the number in the box here, the c value. And we're going to put that number here. So 1 times 3, we're going to put here. Now just be careful here in the long division. At each step we subtracted. Here we're adding. Okay, so just a different technique here. Here we're adding this number together, these numbers together, and getting a 1. And then repeating the process again. 1 times 3, same thing. Adding those numbers together, getting a negative 2. Negative 2 times 3, put here. And this last value here is always going to be your remainder. So that agrees with what we had in the previous example, a remainder of 0. These numbers are the coefficients of your quotient, coefficients of the quotient, beginning with 1 degree less than the dividend you started with. So here we started with a 3rd degree polynomial. So this starts with x squared. So this is the coefficients of the quotient beginning 1 degree less than the dividend. So once again, our answer here, same as it was before, is this. Right? 1x squared plus 1x to the first minus 2. And that was the same thing we got over here. So when you have this form of the divisor, I think synthetic division is the better choice. It doesn't matter if you prefer long division, it just takes longer to do, and there's more work involved. If you get used to doing synthetic division, it's a much, actually you want to get used to doing synthetic division because it's going to come up in future work, and you don't want to have to go through the long division process over and over again when you have this available to you. So whenever you have this form of the divisor, just again be careful with the negative sign. If this was x plus 3, then we would have put a negative 3 up here. And that is long division and synthetic division. Now we're going to use this in what we're going to talk about next, the factor theorem and the remainder theorem. And again, keep in mind what we're trying to do. We're trying to find zeros of functions, which are the x-intercepts, right, where the graph of the function crosses the x-intercept, or the x-axis. That's the goal here. We're trying to divide a polynomial to get one factor, and then use this next technique we're about to learn to find the rest of the factors, which will lead to the zeros, which will lead to the x-intercepts, which will allow us to graph any polynomial function. So let's look at the remainder theorem and the factor theorem. So the remainder theorem says and this is going to be on page 371. So let me take an example from the book here. All right, so let's say we're given this function. X cubed minus 7x squared. All right, so that's a function, and we want to use the remainder theorem to evaluate this function. The question is, we'll call this RT for remainder theorem. Use the remainder theorem to find this function evaluated for an input of 3. All right, now we know how to evaluate a function, right? We can just put 3 into this function and find out the value. That's not what this question is asking. We can do that to check our answer. Like, we can just do that right now. Let's say f of 3 is 3 cubed minus 7 times 3 squared plus 5 times 3 minus 6. So 3 cubed is 27. 7 times 9 is 63. 15 and 6. So let's see, we get a negative 36, negative 21, negative 27. All right, so we know that's the answer to the question. But the idea here is to use what we call the remainder theorem. Using the remainder theorem to evaluate a function for a certain input, we're going to use what we just learned about synthetic division. We're going to divide the given function by x minus that number. And the remainder, therefore the remainder theorem, is going to be our answer to the question. Okay? So we set up the synthetic division, and whatever this number is, that's the number you're going to put in the box for the synthetic division. Now again, important that you put it in descending order and have no missing terms. Put zeros in for any missing terms. There are no missing terms here, so we just write out the coefficients of the polynomial given. And then we go through our synthetic division, and whatever we get here is going to be the answer to that question. Okay? Hopefully we're going to get the same thing that we got when we just put the number in. So we bring the 1 down. We say 1 times 3 is 3. We add to get negative 4. We multiply negative 4 by 3. We add to get negative 7. We multiply negative 7 times 3, and we see that we do in fact get the same value, negative 27. So we know we did it right? But that's the remainder theorem. The remainder theorem says given any polynomial function, if you want to evaluate that function for some input, if you perform the synthetic division with that input as the c value, whatever your remainder is the answer to that question. Okay, so that's the remainder theorem. Now, a special case of the remainder theorem is when this equals 0. So when this equals 0, that would mean that x minus 3, when I divided this polynomial by x minus 3, I got no remainder, which would mean x minus 3 is a factor of that polynomial. That's why it's called the factor theorem. So this is how we're going to determine whether a value like this 3, whether x minus 3 is indeed a factor of this polynomial. So the question could have been worded, is x minus 3 a factor of this polynomial? And you would perform this operation, you'd get something other than 0, which would tell you that no, x minus 3 is not a factor of this polynomial. If this was 0, then x minus 3 would be a factor, and then we could break this down into the linear factor that we just found times the quadratic factor that would be left. And then we would break down the quadratic into two linears, and we'd be back to where we were in 3.2 with a set of linear factors, which would lead to the zeros of the function, which would lead to the x-intercepts. And that's what we're trying to do in this section. So let's look at another example of this and ask all those questions. All right, so I'm looking at number 38 on page 374. Okay, so we're given this function, this polynomial function, fourth degree polynomial function. So 38 minus 5x cubed plus 5x squared plus 5x minus 6. And we want to evaluate that function for an input of 2. And also, let's add the additional question, is x minus 2 also state whether x minus 2 is a factor of the given polynomial. Okay, so two questions. Evaluate this function for an input of 2 using the remainder theorem, and then using that result, tell whether x minus 2 is a factor of this polynomial. So we go through the synthetic division process. We make sure our polynomial is in descending order, 4, 3, 2, 1, constant, so we don't need any zero terms. The number that we're looking for is the C value that we want to put into the box here. And then we list the coefficients, 1, -5, +5, +5, -6. So remember, this number is going to be the answer to this question, whatever we get for the remainder. So we go through the synthetic division process. Bring the 1 down, 1 times 2, adding these numbers together, -3 times 2, adding these numbers together, -1 times 2, adding 3 times 2, and we get a 0 remainder. Okay? So what we've done is we've answered both questions. F of 2 is 0. That's the answer to the first question. And you can check that by putting 2 into this function and making sure you get 0, you will get 0. And because the remainder is 0, that tells us that yes, x minus this number is a factor of the original polynomial. So what that allows us to do, and we won't finish this one, but we'll do another one where we'll actually find all the zeros. But what we've done now is we've broken this down, just like we can break 45 down into 9 times 5, we've now broken this fourth degree polynomial into a linear factor times the quotient that's left, starting 1 degree less than what we started with. So 1x cubed minus 3x squared minus x plus 3. So 1x cubed minus 3x squared minus x plus 3. And what we're going to do, we won't do it with this one because these numbers, we weren't asked to go further than this, and these numbers might be a little ugly. But in our next example, then we'll take this and repeat the process. Break this down, looking for a 0 of this, so that we can now break this down into another linear factor and a quadratic. And once we get down to a quadratic, we know how to deal with quadratic functions, and we would get 4 zeros for this 4th degree polynomial. All right, so that's the idea of what we're doing here in chapter 3.3. The remainder theorem shows us that whatever c value we put here, whatever this remainder is the original function evaluated for that c value. If that remainder comes out to be 0, then x minus this number is a factor of the polynomial and allows us to break the polynomial down 1 degree at a time until we get all linear factors. And once we get all linear factors, we can easily solve each linear factor to get the zeros, the x-intercepts, and that'll help us graph the function. All right, I think that's it for 3.3.